Alright, so collisions and impulse. During a collision, objects are deformed due to the large forces involved. We can determine the relationship between the force, the time it acts, and the change of momentum, often velocity, of the object by using our definition of impulse. So if you remember, impulse equals force times the change in time. We're actually going to skip these next two slides. So now, basically those next two slides say that if no external force acts on a system, its momentum won't change. So remember we talked about how momentum was conserved. We're going to look at three types of collisions. In all cases, momentum's conserved, so we don't have to worry about any impulse. In one case, elastic collisions, energy is conserved. In the other two cases of inelastic collisions, energy is not conserved. Some of the energy might be transformed into heat, bonding, etc. So, during a collision, measurements will show that the total momentum does not change. So, if you look, we have object A, and it's going to object B. So what they did was, as we know, momentum equals mass times velocity. So now they just labeled mass and velocity of A and mass and velocity of B. So what happens is that they go into each other, which is shown here, and then they come back out from each other. So if you think about two balls, they hit, they bounce back out. But now when they bounce back out, the velocities are going to change. So in the beginning, it's just the velocity of A, but then when it comes back out, it's velocity of A prime. Prime just means it's the one after. So then the same thing happens here for B. So if we look, we have our equation here. So this is our, if you remember when we did system of momentum and how you added up both of the momentums of each object. So we add them up in the beginning and we add them up at the end, but the only thing that's changing is our primes over here are changing because our velocities are different afterwards. So as you can see here, momentum's conserved in all collisions. So collisions in which kinetic energy is conserved are called elastic collisions. Those in which they are not are called inelastic. So in elastic collisions, if you look, our arrow going in is equal to our arrow going out in both sides. In inelastic, they lose a little bit, so the arrows are going to change. So just to review, in blank collisions, momentum is conserved. So, as we said, in all collisions, momentum's conserved. In blank collisions, kinetic energy is conserved. So, if you remember what we just discussed, energy is conserved in elastic collisions. And you can remember that. It starts with E. Energy, elastic. It's conserved. More formally, the law of conservation of momentum states that the total momentum in an isolated system remains constant. So the momentum's not changing since it's conserved. So we've got our velocity of our first train here is 4.5, and this one was at rest, so it's at 0. So now when they collide and they're stuck together, we want to know what is the velocity of both of them afterwards going to be. So we have our example here. A 13,500 kilogram railroad freight car travels on a level track at a speed of 4.5 meters per second. It collides and couples with a 25,000 kilogram second car, initially at rest and with brakes released. No external force acts on the system. What is the speed of the two cars after colliding? So what's happening here is we've got our two trains, just like in this picture. They're going to collide together. This one is at rest, but its brakes are off. So that means once it gets hit, it's going to move. So now they're going to be moving together. So the first thing we want to do is list our givens. We know our mass of the first one is 13,500. And it's originally traveling at 4.5 meters per second. 0.5. It collides and couples with a 25,000, so our M2 is 25,000 kilograms. And it's initially at rest, so that means our V2 is 0. And they want to know what is the speed of the two cars at the end. So if we go back to the original equation, we've got the momentum of the first one, so M1, V1, plus the momentum of the second one, m2 v2, has to be equal. Remember how they added in the beginning has to be equal to how they're added at the end because momentum's conserved. So now we've got m1 v1 prime plus m2 v2 prime. So our momentum in the beginning, when they're added together, has to be equal to the momentum at the end. But now there's a couple things we need to do. We see here v2 is 0, which means right here m2 times v2 gets canceled out because anything times 0 is going to be 0. Another thing is that it says at the end that they're coupled together. So that means they're moving at the same speed. So if they're moving at the same speed, that means our v1 prime and our v2 prime are equal. So what we can do is we can get rid of these v1s and the v2 here and just leave it as v prime so that they're both the same. So when we rewrite that, we've got m1 v1 equals m1 v prime plus m2 v prime. And now remember, we want to get the speed of the two cars at the end. So we know that that is our v prime because that's our velocity at the end. So now all we have to do is solve for that v prime. But if you notice, we have it in two places. But what we can do is the opposite of distributive property, which would give us m1 v1 equals, we take the v prime out of both of these. So now we've got v prime times m1 plus m2. And we know if we multiplied that v prime out, we would go back to how it's written here. And now, again, we just want to get v prime, so we would divide by m1 plus m2. And they would cancel out. So now we've got our v prime equals m1 v1 over m1 plus m2. We can plug our numbers in now. So we've got, let's see, 13,500 times 4.5 over 13,500 plus 25,000, which is now going to give us 60,750 divided by 38,500, which in the end gives us 1.6 meters per second. And it's going to be moving in the same direction that the original car was going, because it wouldn't hit and then start going the other way. The brakes were released, they're both going to go. So go through that again. If you're confused, walk through it, and if you are confused, you can make a note of it. So, inelastic collisions. With inelastic collisions, some of the initial kinetic energy is lost to thermal or potential energy. It may also be gained during explosions, as there is addition of chemical or nuclear energy. A perfectly inelastic collision is one where the objects stick together afterwards. There's only one final velocity. So, for example, that's our trains when they hit together and they're stuck together at the end. Another example would be, two ice skaters. One of them is standing on the ice waiting, and then the other one glides into their hands and they skate together on the ice. So another example, a cannonball with a mass of 100 kilograms flies in horizontal direction with a speed of 800 meters per second and strikes a ship initially at rest. The mass of the ship is 15,000 kilograms. Find the speed of the ship after the ball becomes embedded in it. So this is the same thing. We've got our ship there, it's at rest, cannonball hits it, and then they go together. So our M1 is 100. The velocity of it is 800. Our M2 is 15,000. And our velocity of the ship in the beginning was 0. So again, now we're looking for V prime. We're looking for the velocity of both of them together at the end. So again, we start with our M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. And again, our v2 in this case was at rest, so we can cancel that out. And we know they're coupled together at the end, so we can change the v1 prime and the v2 prime to just v prime. So m1v1 equals m1v prime plus m2v prime. And again, we're solving for v prime, so we're going to do the opposite of distributive property to get it by itself. This is just like the last problem. And then we're going to divide. So now that we've got our equation, we can plug our numbers in. I just want to make sure I wrote it correctly over here. So now, I apologize. I wrote it wrong. Not multiplying these. We're adding them. I just wanted to make sure I wrote it right on the other one. So now, we've got 80,000 divided by 15,100. Which in the end is going to give us about 5.29 meters per second. All right. All right, so the next one has a 40-kilogram girl skates at 5.5 meters per second on ice towards her 70-kilogram friend who's standing still with open arms. As they collide and hold each other, what is the speed of the couple? So this is just like the previous two problems, and this is the example I gave. You know, you've got your ice skater on the ice, they go into each other, and then they skate together. So I want you to try to solve this one on your own. I will give you the answer so that you can see if you got it correct. So it should come out to 2 meters per second. All right, conservation of momentum. So momentum conservation works for a rocket as long as we consider the rocket and its fuel to be one system and account for the mass loss of the rocket. So in the beginning, our momentum was 0 because the velocity was 0. And then as it goes up, in the end, our momentum of the gas goes down and pushes the rocket up and gives it its velocity. All right, elastic collisions in one dimension. Here we have two objects colliding elastically. We know the masses and the initial speeds. Since both momentum and kinetic energy are conserved, we can write two equations. This allows us to solve for the two unknown final speeds. So if you notice, over here we've got our original velocity of object, the A, and of object B. This is a bigger arrow, this is a smaller arrow, and if you notice in the end, velocity of the first one is a little shorter than the velocity of the second one. So let's see. What they did was they took both equations, they distributed, they did the opposite of the distributive property, and what they worked out to get was to cancel out the masses, and what you get is that in elastic equations, where energy is conserved, the velocity of the original one, of the first object, plus its final velocity equals the final velocity of the second one plus its original velocity. So for all elastic collisions, the magnitude of the difference of the velocities is the same before and after a collision. Physically, v1 minus v2 is the relative velocity that the objects collide with. It's how fast they're approaching each other. And v2 prime minus v1 prime is the relative velocity of their separation. It's how fast they're going apart after the collision. For all elastic collisions, regardless of the masses of the objects separate after the collision with the same velocity that they collided with. So the difference between them is always going to be the same. They're going to hit together and they're going to go apart always with the same velocity. So we just have a chart here of our collisions, just in case, and if you want to study for your test. So inelastic has momentum conserved, energy is not conserved, and they don't stick together. Because remember, that's the one that it might have heat. Perfectly inelastic, so if you think of a perfect figure skater, momentum's conserved, energy is not, but they do stick together in the end. Elastic has momentum conserved, just like the other two. Energy is conserved. If you remember, it starts with an E, so does energy, and they don't stick together. So those are the ones that push apart. So two objects have an elastic collision. Before they collide, they are approaching each other with a velocity of 4 meters per second relative to each other. With what velocity do they go apart from each other? So if we've got our our V1 equals 4 meters per second. And if they're relative to each other, that means that they're going to be moving opposite. So if they're going 4 meters per second towards each other, that means that the first object is going in the positive direction, but then the second object is going to be going in the negative. So the V2 has got to be negative 4 meters per second. So with what velocity do they go apart from one another? Well, now they're just going to switch because they're going to hit here, and then they're going to go in the opposite directions. So V1, this original object, is now going to be going in the negative. So now it's going to be going in the negative 4 meters per second. While V2 prime hit and is now going back in the positive direction. So 4 meters per second. Two objects have an elastic collision. One object, M1, has an initial velocity of 4 meters per second, and M2 has a velocity of negative 3 meters per second. After the collision, M1 has a velocity of 1 meter per second. What is the velocity of M2? So, we've got V1 equals 4. V2 equals negative 3. We've got V1 prime equals 1. So now we want to get V2 prime. So we have got over here now V1 plus V1 prime equals V2 prime plus V2. So now if we want to get V2 prime by itself, we've got to subtract V2 from both sides. So now we've got V2 prime equals V1 plus V1 prime minus V2, which is going to be, our V1 was 4, our V1 prime was 1, so 4 plus 1, minus V2, which was negative 3. So now we've got minus and negative, which makes one big plus sign. So our V2 prime is going to equal 4 plus 1 is 5, plus 3 is 8 meters per second. Alright. Elastic collisions. For elastic collisions, regardless of the masses of the objects separate after the collision with the same velocity that they collided with. So if you notice, we don't even have mass written in there. In a head-on elastic collision where one object is much more massive than the other, the velocity of the smaller mass after the collision will be about twice that of the projectile, and the projectile velocity will be essentially unchanged. So if you think a bowling ball and a ping pong, it's huge compared to this tiny little plastic ping pong. So a bowling ball has a velocity of plus v when it collides with a ping pong ball that is at rest. The velocity of the bowling ball is virtually unaffected by the collision. What will be the speed of the ping pong ball? So, so we've got that our V1, our bowling ball velocity is v. Our ping pong ball, V2, is at rest. And then in the end, the bowling ball is virtually unaffected by the collision. So that means that our V1 prime is still probably v. So if we have our equation, v1 plus v1 prime equals v2 prime plus v2, and we want to get v2 prime, we want to get the speed of the ping pong ball at the end. We're going to subtract a v2 from both sides. So now we've got v1 plus v1 prime minus v2 equals v2 prime. We know our v2 is 0, so we can cancel that out. So our v1 was v plus our v1 prime, which is also v, equals v2 prime. So v plus v gives us 2v. So if you think about it, basically our bowling ball is going to hit the ping pong, and the ping pong, which is so much less, is going to be going double the speed of the bowling ball. It's going to get hit and then just go flying double the speed. Oops. Alright, so now the same thing. We've got a baseball bat, has a velocity of plus v. When it collides with a baseball, that has a velocity of negative 2v. The bat barely changes velocity during the collision. Our baseball player just keeps hitting the ball. What will be the speed of the baseball? So we've got v1 was positive v. Our baseball had a velocity of negative 2v. And our baseball bat, v1 prime in the end, just keeps going. It keeps swinging through. So it's also still v. And we want to find v2 prime. So we've got v1 plus v1 prime equals v2 prime plus v2. So now, again, we would subtract v2, and we would get v2 prime equals v1 plus v1 prime minus v2. Plug our numbers in, and we would get v1 is v plus v minus negative 2v, which becomes 1 plus sign. So v plus 2v is going to give us 4v. Alright, so now those were all things with different masses. So now we want to know what happens when they are the same mass. So in that case, if they are the same exact mass, and this is only true if they are identical masses, your v1 prime is equal to v2, and your v2 prime is equal to v1. So basically what happens is the one object hits, and this object hits. So this is object 1, this is object 2. When they hit, over here, this one is the original one, the first mass is going to go out with the same velocity this one hit it with, and then this second one is going to go out with the same velocity that this one hit it with. So they basically mirror each other. So two objects with identical masses have an elastic collision. The initial velocity of m1 is 6 meters per second. So our v1 equals 6 meters per second. And m2 is negative 3 meters per second. So our v2 equals negative 3 meters per second. What is the velocity of m1 after the collision? So we are looking for v1 prime. Well, we know it's equal to v2, so that means our v1 prime is equal to negative 3 meters per second. And that's all you have to do. So now the next one says, all right, what is v2 prime? What is the velocity of m2 after the collision? Well, we said back here that v1 was 6 meters per second, so that means that v2 prime is equal to that, which is 6 meters per second. All right, so now 24. Two objects with identical masses have an elastic collision. The initial velocity of m1 is 3 meters per second, so v1 equals 3 meters per second. And m2 is 2 meters per second, so v2 equals 2 meters per second. What is the velocity of m1 after the collision? Okay, so that's v1 prime. Well, if our v2 is 2, so that means our v1 prime is 2. And I can guess the next problem, as you can see, is asking for velocity of m2, which is v2 prime, which we know is equal to the original velocity of object 1, so v1, which if we look back here was 3. So v2 prime equals 3 meters per second. I know there was a lot of information in this packet, so what I need you to do is go on Edmodo, tell me what you understood, what you didn't understand, and what you need help with.